Hello, my name is Bryan Mathews, and today I will be teaching the topic R2.3.5, the reaction quotient, that is a part of the chemistry HL syllabus. So, first of all, let's talk about the difference between the equilibrium constant and the reaction quotient. The equilibrium constant over here was previously discussed in the unit before, and it basically states it's a constant that represents the reaction position in the position of equilibrium in a reaction. And Q, the reaction quotient is related to this. It states the position of a reaction. However, the only difference is that it is not in equilibrium. So let's take a look on this side over here. For the example reaction, we have the formula for Q over here, and this is really important to remember as this is not in the data booklet. And it is the same as the equilibrium constant formula, but the concentrations are not in equilibrium, which basically means that these concentrations are given at a particular point in time of the reaction that's not when equilibrium has occurred yet. So as we can see, it's always the concentration of products over the concentration of reactants, as C over here and D over here, and the coefficients are always powered and always multiplied and not added. So that's obviously really important to memorize because it's the same for QC, but QC is for at equilibrium concentrations. So now let's look at this column over here, or this group, sorry. So I have three different scenarios here. There's only three possible scenarios in these kinds of IB questions. So one scenario they might give is when Q is greater than QC. So over here, I have a table or a line graph that could try and help that I've done because this is how I vision it in my head. So over here, Q is greater than QC. Let's look at the first example. Q is greater than QC. So Q is greater than QC, just like that. And from the previous unit, Le Chatelier's principle just states that when there's a change in a reaction, like either more products are added or any etc., the reaction will always form a new equilibrium. So Q is always going to want to go towards equilibrium. So Q wants to go down. Q will always want to go down because Q's goal is to always be at QC because QC is equilibrium and the reaction wants to go to equilibrium. So Q always wants to go to equilibrium. That's how I remember. And so if Q wants to go downwards, if Q wants to decrease, let's look at this formula right here. Q wants to decrease. What could be changed in this other side of the equation? Well, if Q is decreasing, that means that either the products are decreasing or the reactants are increasing, which is actually happening at the same time because of obviously for the denominator it's the inverse. So that means that since it's P over R, the concentrations of P over R, that means that the concentrations of the reactants will be increasing. And over here it is means that the reaction proceeds to the left, and left is for the reactants, so the reactants increases, and yeah, that's how I imagine it. So let's do it for the other scenario now. Q less than Kc, so Q will be over here, and Q wants to increase because it wants to reach equilibrium. And now, if Q wants to increase, what could be done to this equation? Q wants to go up. So products wants to go up, reactants wants to go down. And that's exactly what happens here. It proceeds right. It means that it's favored towards the products, which means that the products are increasing. And there you have it. And Q equals Kc just means the reaction to equilibrium, just like this. Because yeah, it's not changing and it's already at equilibrium because Qc is the equilibrium constant. So when given a reaction quotient problem, how would you solve it? The only thing you have in your toolbox, and also information from the previous units, is using an ice chart. And over here's an ice chart. This is what it looks like. Ice stands for initial, change, equilibrium. And so you lay out like this. This is an example reaction right here. And over here, you can see I put an important note. Use for change, use the molar ratios because this is really important. We've learned this in stoichiometry. unit in balancing equations and using mole ratio. And what I mean by this is, let's assume that the reaction is a forward reaction over here. We know that the change, this is what the change rule, right? The change will always be, okay, there's two different things that could happen. First, for the forward reaction, we know that these signs are going to be negative and this one's going to be positive, because for the forward reactions, products are being produced. So products will be plus and the reactants will be minus. That's the first thing. And secondly, right now we don't have any numbers, so we're going to assume that x is the change. The changes over here will be as follows. Because, look at the mole ratio. There's 2 here, and there's 1 here, so that's 1. And this one has 2, and that's 2x. So this is what I mean by using the mole ratios, is that the change, we have to look at the coefficients to balance that change over there. And so now let's move on to a sample problem. This is if you can solve this problem, I think that, in my opinion, from my past experience, especially in after having done the May 2025 chemistry exams, I think that this problem is pretty an accurate representation of how well you would do with reaction quotient questions, because the reaction quotient questions are not exactly hard, but if it's a skill to do them really fast and really accurately. So let's start by filling out the ice chart. So we have PCl3 initial, which is this box right here, and that's 0.1. Then we have Cl2 initial, which is also 0.1. And then PCl5 at equilibrium is 0.72. And Kc, we just know Kc is given is equals to 5 times 10 negative 2. Okay, so over here, remember, okay, first thing we need to do is look at the coefficients to write in the change columns, even though we can substitute it with x and unknown because we don't know that yet. All the coefficients are 1, which means that the changes are always going to be x. And so let's assume that it's a forward reaction right now, because in reality, if it's not telling you what whether the reaction is forward or negative, it's just always best to assume the forward reaction. And if you have a value that doesn't make sense, then you know it's opposite. And what I mean by this is that if the equilibrium is either doesn't match up with the initial, like, you will be able to understand that. But for now, since this is given, we should always assume first that if it doesn't tell us, that the reaction is proceeding forward. And so if it's a forward reaction, the reactants are going to decrease. So this will be a minus and this will be a plus because products are being formed. So what's the first step? Since we have this, let's start with the Kc. So using all of this information, we can form a equilibrium constant equation. And so let's start by filling the equilibrium row, because this is what we need to find Kc. So we know that initial is 0.1, and then the change is plus x, so the equilibrium concentration would just be that, and same thing for this. Let's form an equation for Qc. Qc equals products, remember, products, which is PCl3 multiplied by concentration of Cl2 over concentration of PCl5. And so we know that this is 5 times 10 to the negative 2, and let's fill in the blanks. So we know that PCl3 is 0.1 plus x, and then since that the PCl3 and Cl2 are the same, let's just square that. And then over here is 0.720, because that's what equilibrium is for PCl5. So solving for x, after using my calculator real quick, we get x in the end, after doing all this equation, simple algebra, and rearranging, we get x equals 0.0897. So this is the change in the concentrations. And so now the question is asking for calculate the initial concentration of PCl5. So what we can do now is find initial equation of PCl5. So that's what we're asking right here. And so how do we get from equilibrium to change to initial? Well, it's simple, because we know that PCl5 initial equals to, since we have equilibrium, 0.72 plus x, because we're just doing the opposite here. and that would be equal to, after doing the math, it is 0.810 mole dm negative 3. So there you go. That's your answer. And yes, so even though this question doesn't specifically talk about the reaction quotient, it does apply principles because like right here, Q 0.1, 0.1, this is all reaction quotient because it's not at equilibrium. So even though the question doesn't specifically talk about the reaction quotient, the concept is there, and we know that this is your cheat sheet right here. And so these are all the key facts that you need to know in order to score in every other these kind of ice table questions. And yes, that's it for this lesson, and thank you for listening. And yeah, I hope this explanation gave you a better understanding of the reaction quotient.